All right, so this is one of the most fun topics in Calc 1. The idea where we take, in a second here, we'll take the limits together so that we can start getting exact answers on things like where we fiddle around with average rate of change and instantaneous rate of change. We can get exact answers on moving targets. So we can measure rates of change exactly, which is one of the big tool of calculus. And so we're going to use limits to get us there. But at first, we just want to look at the idea of what we're doing. So building it up here. What we did for the average rate of change problems was we had a function and we took 2 points and we figured out the slope between them. Or another idea for that, right? Like a point here and a point here is called the slope of the secant line. So the average between 2 points. And then just so the notation works out nicer, we can, instead of just calling this like point A and point B or point A and point X, we can call it A. And then since the other point is a little distance away, we can call it A plus H. So if this was like 3, this might be 3.1 or 3.5 or 4, right? This is a point, and this is a point a little ways down the road. So one of them is at A, the other one's at A plus some random amount. And so what we're going to do is, if we start getting these 2 points closer to each other, or a secant line becomes like a better estimate of the slope at the point that we're looking for. And so here's that kind of in a static mode. If it lets me move my screen. There we go. So here we're just doing a comparison. Like, what if we start moving those points closer and closer and closer together? So here we have, right, A and X1, then X2, then they do another one maybe right on top of it. Or they're just saying like, here's a point and here's a point down the road. Or if we do this point and a point a little bit closer, and our goal would eventually be to have them right on top of each other. But remember from earlier from our instantaneous rate of change, if we put them right on top of each other, we end up dividing by 0, right? Because our difference between the two x values is 0. But notice if we do this A plus H thing, we're trying to subtract our two y values, so rise over run. So if I say one of my y values is the y value of the point down the road, it's f of a plus h. It's what I get when I put a plus h, the second point into the function, minus what I get when I put the first point into the function. And then the bottom is the difference between my two x points, right? So a plus h minus a. And notice every time you do that, a plus h minus a, the a's will cancel. You're just left with h. H is like the x distance between your 2 points. So this is automatically slope, right? It's rise over run. And then this is where the trick to get them really like infinitely close together, right? So we have this tool now, is that we take the limit. So the limit as h goes to 0. We're getting these points infinitely close together. This gets us around the dividing by 0 thing because we can start using our limit tools to try to take this limit and get the slope at that exact point. So notice if h is how far away the 2 points are together, the distance between them, if we take the distance between two things to zero, we've essentially got them infinitely close together, so they're basically right on top of each other. So we have 1 point, we have a point nearby, we just keep getting it closer and closer and closer and closer and closer and closer, or like here, closer and closer and closer and closer and closer and closer until we're like infinitely close, so we might as well basically be right on top of that same point. And so that's what it looks like to take the slope at a point. And so the definition of the derivative at a point is we take the slope between 2 points x and a, or a lot of times, right, so that things cancel out nicer, and when we get to the algebra of it, we'll use a point and a point nearby, so a and a plus h. And so we're taking the slope between 2 points, but then we're taking the distance between those 2 points to 0. Then also, if you can do this at individual points, you could do it at every single point of a function, and you could come up with a whole new function known as the derivative that represents the slope of the original. We're going to spend about half the class dealing with this in one way or another. So if I have a point anywhere on the function and a point a little bit further away from that, so x and x plus h, so a point down the road, and h is the distance between those 2 points, right? X is here, x plus h is over here, and then I take the limit, so I get them infinitely close together. All right, so what does this look like to actually do it with a function? We'll start out with a really simple function, just so the algebra works out nicely. So let's say f of x is negative 5x plus 2. I'll cheat a little bit and mention, since technically what we're doing is finding the slope, you can tell already that this is a line. And since it's in y equals mx plus b, the slope probably should be negative 5. So maybe I kind of know my answer before I start. That's not always the case as the functions get more difficult. But in this one, maybe it's kind of nice to see that before we even get going. But then we want to show that that's true. We want to take the derivative of this function using the definition. So we want the limit as h goes to 0 of f of x plus h. So notice for functions, right, that means where there used to be an x, put an x plus h. If our function is negative 5 times something plus 2, then we're putting x plus h in there for our something. So there's f of x plus h, right, what the function looks like when you plug in x plus h minus the original function. Be careful, you're subtracting the whole thing. So if you have more than one term, that means parentheses. So we have f of x plus h minus f of x and all over h. So now we have it set up, we just want to see if anything reduces. So I'll probably distribute here and distribute this negative in here. So limit as h goes to 0 of negative 5x minus 5h plus 2, and then negative negative makes this plus 5x minus 2, and then all over h, and then we'll see if anything cancels. It looks like minus 5x and plus 5x add to 0, plus 2 and minus 2 add to 0, and so now we're left with the limit as h goes to 0. My arrow got a little crazy there. Of negative 5h over h. So then we also might notice h divided by h, right? There's a common factor cancels out. And so now we're just left with the limit as h goes to 0 of negative 5. And then that's a pretty easy, since it's a constant number, it's a pretty easy limit to take. The limit, no matter what we do with h of negative 5, is just always negative 5. If you have a more complicated function to start with, you'll end up with a function as your answer. But notice, kind of like we expected here, and if I want to write the whole thing out, the derivative of this function is negative 5, meaning no matter where you go on the original function, we kind of pointed this out in the beginning because it was a line, the slope is always negative 5. So every single point on the line has the same slope. No matter where you go on the line, the slope is always negative 5. They won't all be algebraically that easy, but in the beginning, we want to take examples that work out nicely. So there's the idea behind the derivative, and one example of simplifying an easier one. We'll get some more interesting ones in there eventually too.